just one little warm-up question we have for today. We are missing a few of our classmates, so I am going to record this today just in case they want to take a listen. Okay. So, number one, which was the only number, write an equation to represent the following: a quadratic function whose vertex is the point -2, 5, that is reflected over the x-axis and is vertically stretched by a factor of 2. So, since I've given you all these nice pieces that fall nicely into vertex form, let's put them in. Oops, this should be a plus k. So when we're in vertex form, it's always x minus the x value. So minus a negative is going to make a plus 2. And then the 5. It's reflected over the x-axis, which is going to put a negative out in front. And it's stretched by 2. So there we go. Did y'all use f of x instead of y? Yeah. All right. Beautiful.
When would it be the opposite?
I tend to go
like, when would it say, oh, it's stretched or whatever by 2, but then you actually put like half?
Okay, that's when we do anything horizontally. We always do the opposite, whether it's a horizontal shift or horizontal scale change, stretch or compression. You always would do the opposite. So if it had said it was horizontally stretched by a factor of 2, instead of multiplying by 2 in here, we would divide by 2.
Or 1/2.
Or multiply by 1/2, yeah. But this one was vertically.
And you would put that in the parentheses or outside?
It would go inside the parentheses with your x. It certainly would. Honestly, what you'll see the most of is the vertical stretches and compressions. Because a vertical stretch looks like a horizontal shrink, doesn't it?
Yes.
So most of the mathematics textbooks and the mathematics resources that I've looked at really stick mainly with the vertical stretch and compression. Now I'll throw in horizontal just so we have some exposure to it, but the vertical is what we generally see. Okay, let's take a look at our homework and talk about how we got this graph. Now, the way I got the graph was I said, okay, the vertex is the opposite of this. This stays the same. So my vertex is going to be at 3, 256. Now I'm just kind of estimating where 256 would be. And then what I did was I plugged in 0 for x. And I plugged in 0 for x. I got out 112. So we know it's about 112 here. So aren't all quadratics symmetric? So if I have this point, can I just flip another point right over here?
Yeah.
This equivalent amount is what I should have done. All right, the other way you could do it is go over 1, go down 16. So that would, I did a terrible job with my graph here. Let me try it to get through here a little better. There we go. That looks a little better. All right. Did you label your axis?
There it is.
And we have counting numbers here. Now these counting numbers are a little trickier because we're counting by ones on our horizontal axis, which represents time in seconds. And we're counting by 30s because they already established the counting number for us. 30s is probably not a counting number I would choose, but they had already established it by naming this 60. So each tick mark represents a 30-foot interval in height. So for B, how high will the firework be when it reaches its highest point? Well, if something is modeling a quadratic function, or if it can be modeled with a quadratic function, then the vertex of that quadratic function will either be the max or min. If it's a quadratic that opens down, that vertex will always be the max, the maximum point. If the quadratic opens up, then the vertex will always be the minimum point. So because it's worded when it reaches its highest point, well, that's going to occur at the vertex. And we can see from the equation the vertex is the point 356. So the highest value of the function is not 3,256, is 256 feet. All right, C. What is the height above the tower from which the firework is launched? All right, so it's sitting on the tower at time 0. So that's what the y-intercept is, because the y-intercept represents time 0. So if we plug in 0 here, did you get out 112? So it's 112 feet. And the way we do that is by plugging in 0 for the time. Okay, now this one. Which quadratic function has a lesser min? The function who has a graph at the vertex of -5, -1, or the function graph below? Well, the minimum value of this function is -3. The minimum value of that function was -1, so the graph is lower. Make sense? All right, let's take a look at your bookwork. Now, first period, all came to an agreement that I forgot to write on the board, describe the characteristics for the graphs. So when I checked the homework, I did not account all for that. But if you had pulled my calendar up off the website, it is typed correctly on there. So the calendar is on the website, and I just failed to write that on the board Friday, so I did not make you responsible for that. But we do need to become very familiar and be able to name all these characteristics quite quickly. So take a look at that and see if you had any questions about the characteristics on 23. Had you written them down, could you have done it? And when we say min there on 23, if that's at what point does the minimum occur? The minimum value would just be the -3. Yes, sir. Yes, sir.
When it asks what point the maximum or minimum occurs, would it always be the vertex?
It is. Yes. The vertex is always in a quadratic will either be the maximum or the minimum function. Just depends on how it opens. Okay, any questions on 23, 29, or 30? And Mary Grace, did I hear your name called on the announcements? Congratulations. Do y'all listen to the announcements?
No.
No, so you have absolutely no idea.
She's homecoming court.
Oh, never mind, you do know.
Nice.
She just knows.
Well, that's the only possible. Okay, never mind.
I wouldn't say the only, but
All right, let's move on. Okay, here's 35, 38, 39, 40, and 41. Take a look at those, see if you have any questions.
Must have been a riot.
That first one was right.
I'm kidding. I'm kidding.
is it really?
Yeah, 25 and
No, because my directions should have said, give the characteristics. And my directions did not, because I forgot to write that on the board. Your homework was on page 498. Which question are you having? 35. Right. 35 asks you to describe the transformations. And so what you probably wrote was the parent graph is shifted down to, and it's vertically stretched by a factor of 4. And then on 38, what you should have written was there is a horizontal stretch by a factor of 3, and it's reflected over the x-axis. So on 35 and 38, if you had just followed the directions in the book, those would have been your two answers. So for 35, once again, if you were following the directions in the book, because I forgot to write it on the board, it's shifted down 2 units, and it's a vertical stretch by a factor of 4. And 38 would be a horizontal stretch by a factor of 3 and reflected over the x-axis. Give that to me.
Right.
And anything else that might distract you.
Do something Mr. Didier taught me. I apologize.
No blaming Mr. Didier. Okay, any other questions? All right. So we're pretty familiar with vertex form at this point. Didn't we spend 2 days on it? Yeah?
I'd say so.
Vertex form. So this is vertex form. Y equals A times X minus H plus K. And we get our vertex. It's always the opposite of what's with our x. What's added to the end is our y at the vertex. So we can describe the vertex as hk. Now today we're going to look at standard form. So let's see how we could take vertex form and get it into standard form. Do you guys know that standard form is ax squared plus bx plus c?
No.
So we have our squared term, we have our linear term, and we have our constant. And so that is standard form for a quadratic, y equals ax squared. Now, this is a little trickier to graph and display graphically. So we're going to talk about how can we relate this back to this, because this is really easy to graph. Vertex, out quickly, we can look at how we would have to change those squared moves from the vertex. So these are notes. And I was waiting for you to write down this part. That's why I just kept talking and talking.
Okay. I apologize. I zoomed out again.
And when you're ready, leave some space in between because we're going to make this turn into this. So let's see how these two relate. If I could take vertex form, and do you see I have a binomial squared right here in the middle of my vertex form? Let's go ahead and expand that binomial. So to expand that binomial, we're going to square that first term. So x squared is just x squared. And we're going to double the product of the two. So x times negative h is negative 2hx. Does that make sense?
No.
Remember we said you could square the first term, double the product of the
It's
two.
going to be x minus h, and then you just...
Yes.
And plus h squared.
Okay, and then plus h squared, because when I square the negative h, I get a positive h squared. And then we still have that plus k sticking at the end. So step one is to expand the binomial. Then we'll distribute the a through. So we get y equals a times x squared minus 2ah times x plus a h squared plus k. Okay, do you see how when I expanded that? The first term, this quadratic term here, they're exactly the same, aren't they?
Yeah.
So whatever the a is when it's in standard form would be the same a that you would see here in vertex form. Okay? Now, here's my linear term right here. Are they exactly the same? No, here I said I have b times x, and here I have negative 2ah. But for these to be equivalent, wouldn't this b have to be the same thing as that negative 2ah? Okay, so b is going to have to equal that negative 2 times a times h. And this part right here, this doesn't have an x with it, is it? This is just the constant. So those two things are equivalent. Now, I'm going to stick with this one. The fact that we know that b is equal to negative 2ah. Because do you see if I solve this for h, what does h represent? H is the x value at the vertex, isn't it? gives us the x value at the vertex. It also gives us the x value for that axis of symmetry, because x equals 8 is our h is our axis of symmetry. So if I took this and solved for h, the way I'd solve for h is to divide both sides by the negative 2a. So do you see you get negative b over 2a is equal to h. So when I give you an equation in standard form, if you wanted to graph it quickly, if you wanted to find what the x value at the vertex was, all you'd have to do is take this b, the coefficient of your x, do the opposite of it, and divide by 2 times the coefficient of your square term. So let's see if this really works. Let's say I had this equation right here. Okay, this is in vertex form, right? So where's the vertex?
2, 2.
2, 2. And is that going to be the maximum or the minimum value of the function?
That's the minimum.
It's going to be the minimum. How do you guys know it's the minimum? That's right.
Because it's not reflected.
It is not reflected. This parabola opens up, this quadratic opens up, so that vertex is going to be the minimum point of the graph. So this is at the min, and this is what it looks like. All right, so if I were to square this, let's do it real quick, if my movie will work with me. So if I were to square this, do you see I'd get x squared minus 4x plus 4 plus 2? So isn't that this equation? X squared minus 4x plus 6? All right, so now let's try it this way. If I took this equation and did negative b over 2a, and I'm trying to find the x value at the vertex, if I did negative b, what happens to when I do the opposite of negative 4? I get positive 4 over 2 times 1. What's 4 divided by 2? 2. Is that what I had as an x value at the vertex there? Yeah. Okay. So I got the same thing. How would I find the y value at the vertex if I knew the x value?
Plug it.
Plug it in. So do f of 2. And so we'd get 2 squared minus 8. So 4 minus 8 is negative 4, plus 6 is 2. So we get the vertex 2, 2. Did I get the same thing? You see how it works?
I'm confused with the h equals 4 over 2 times 1 equals 2.
Okay, what I did here was my a is the coefficient of my squared term. So a is an understood 1. My b is the negative 4. So when I get into this negative b over 2 times a, the opposite of negative 4 is positive 4. And 2 times the 1 gives me the denominator here.
2a is negative 4. Wouldn't it be negative 2 then?
It'd be negative b, which
Oh, it's
makes
either
it,
b, which is negative 4. So.
okay?
Okay.
All right. So let's look at this one. I'm not going to give you the vertex form, but let's see if we can put this one in the right form. Let's see if we can come up with the vertex and graph it. All right, so this is in standard form. We just talked about a nice little shortcut which gets us to the vertex. What was that? The x value at the vertex is equal to the opposite of b over 2 times a. So this is my A, this is my B. So if I did the opposite of B, what would that give me? 4 over 2 times my A, which is 2. So what is the x value at the vertex? 1. All right, now find that y value at the vertex. Okay, what y'all get? 3? Okay, so if we were going to graph this, we'd go over 1 and up 3. Now look at this equation. The A is 2. It's a positive 2. So how is this quadratic going to open? Up or down? Up, because it's positive. And what does that 2 do to our moves?
Vertical stretch.
It causes a vertical stretch. So instead of going over 1 and up 1, I go over 1 and up 2. Instead of going over 2 and up 4, I'd go over 2 and up 8, way off my graph, so I'm not even going to draw it. Now, on a quadratic, it's always symmetric about that axis of symmetry, which passes through the vertex. So if I did over 1 and up 2 on this side, I automatically do over 1 and up 2 on this side. Did y'all start doing that when you were graphing it? You just made it symmetric? Do one side and then flip it across that axis of symmetry and get the other side? Okay, do that. That's a nice little shortcut. Yes?
Is it obvious, or like, why do we plug in 1 for the x, like when 1 is 8?
Because we got the x value at the vertex is 1. So what is the corresponding y value with that x value? So if I plugged in the x value, it kicks out the y value. If I evaluate the function at 1, that gives me the y value that corresponds to that x value. That gives me the ordered pair.
Wait, so h is the x value?
H is the x value at the order. Like when we started vertex form, we said the vertex is represented by A. So H represents the x value at the vertex. Yes, ma'am.
Hey, this is probably like really super question or something. But how did you get 3?
Yeah, that's what I was hoping.
I got 5.
I got 5 too. Yeah, I got 6.
I got 3.
I got-
Because
Okay, 2 times 1 is 2.
I got
Minus 4, negative 2. Plus 5 is 3.
But
what about the square? So there's no way. It's 6.
What am I squaring? Okay.
Never mind. I multiplied first.
So it's not 6.
It's 3.
That's
Wait, so
Square
what's
the
the
2.
Okay. All right. So let's see if we do every. First of all, let's see if we can now write the equation in vertex form. So remember, vertex form is y equals a times x minus h squared plus k. Do we know our h and k? Yeah, 1 and 3. So it's going to be x minus 1 squared plus 3. And what did we say a was? It's the same. A is the same. So if the a here is 2, the a here is 2. So this is the same equation, but written in vertex form. All right, what would the domain of this be?
negative infinity, positive.
Negative infinity to positive infinity. Range.
Bracket 3 infinity.
Good. 3 to infinity. X-intercepts. Does it cross the x-axis?
No.
None. Y-intercept.
0, 4, 5.
5. Look at this right here. What was that?
5.
Because if we plug in 0 for x, don't these first two go away? So what does C end up being every time? The y-intercept. When I give it to you in standard form, C is also your y-intercept. Because if you plug in 0 here for x, all you're left with is the c part. Does that make sense? Okay, so the y-intercept is 0, 5. It's the point 0, 5. Or you could just say the y-intercept is 5. Okay, intervals where this function is increasing.
From 1
Yes.
to infinity.
Good. Interval over which this function is decreasing.
Negative infinity to 1.
Negative infinity to 1. Interval over which this function is positive.
Always.
Always. So is there an interval where the function is negative? No, there is no such interval.
Negative.
Okay. If I guess you could describe it as the empty set because there is no interval. Let's see. What else did we do? Increasing, decreasing in behavior. And I am going to let you write it this way. As x approaches positive and negative infinity. Because for a quadratic, both ends do the same thing. On this one, y approaches positive infinity. Yes?
Is there a way to graph I on a coordinate plane?
We can't graph it on the coordinate plane. We'd have to graph it on the complex plane.
What?
We're not doing that though.
Is it like a
Yes.
Yeah, awesome.
No. Okay. Questions?
They're all triangles.
All right. We're good? Okay. Let's flip over to, what page is this? Y'all probably want me to tell you. I think my book's open to it anyway. Page 343. And we're going to do a few of these together.
Is that correct? So when it's a horizontal shift, it's going from the blue one outwards. The depression is going like that. The vertical shift is stretches out here. Cool.
Thank you. All right. So on these, we're asked to identify the axis of symmetry for the graph. Well, if these are quadratics that open up or down, the axis of symmetry is going to always be x equals, and whatever the x value is at the vertex. Now, the first one is given to us in standard form. So how do we find the x value at the vertex? In standard form, we do the negative b over 2a. So if we did negative b, it would become a positive 4 over 2 times a. A is an understood 1 here. So we get that the axis of symmetry is x equals 2. You try number 2.
You multiply it by 2, right? Or is it multiplied by 1? 2.
No, wait, for which part?
2a, yeah, 2a.
Yeah, the bottom.
Negative 16. Over 16. What is that? 3/4.
That's 2 fifths. No, that's 3/4.
3/4. That's right.
Okay, so we did negative 12 over 2 times negative 8. So we get negative 12 over 16, which simplifies to 3/4. Okay, now this is back in vertex form.
Yeah.
So let's not forget, it's going to be x equals, what is
Negative 3.
negative 3. Much easier, isn't it?
Is it a negative 3/4?
We always do negative b, which makes it a negative 12 over 2 times a, 2 times negative 8. So we get negative 12 over negative 16, and those negatives will cancel.
Thank you.
Okay, number 4. Will this one open upward or downward?
Downward.
Downward. Okay, the axis of symmetry is going to be x equals, and let's
1.5.
good, 1.5. You can just write 1.5 or 3/2, either way. Okay, so how would we find our vertex?
Plug in the x.
If we plug in the 1.5 for x,
Here.
most of you are not sitting with a calculator, so I'll just give it to you. If you plugged in 1.5 for x, you get out 3.25. Okay, and what would the y-intercept be? 1. So we go over to 1.5, go up to 3.25, and we're estimating a little bit here because we're halfway in between and a quarter of the way in between. But then we have a nice point right here, 0, 1. Can I just do the symmetric? Go right over that axis of symmetry and plot another point. Didn't even come close. But I can move it. Okay, so just right over. This is 1.5 units this way, 1.5 that way. Would put it right there, and then I can draw in my graph. Any questions?
No.
Okay, you try. Number 5.
Miss Wilby, I don't understand how you got the graph.
I'll hold off on the graphing until everybody's graph together. Okay? Okay, were we able to tell from the equation that this one opens upward? No? Okay, let's look right here. Look at your A. Do you see that that is positive 2?
Yes.
When A is positive, your quadratic will open up. So that's how we know it opens upward. Did you get the axis of symmetry as x equals -1 by doing the negative b over 2a? If you plug the -1 in, you get out -4. And our y-intercept is the -2. So, and if you want, you could write it as an ordered pair. So we have a vertex at the point 1, -4. My y-intercept is 0, -2. And so if I reflect right over this axis of symmetry, I get another point there. If I wanted, I could do my second moves. And then I would graph. So I start with my vertex, and I can plot another point, do it symmetric across the axis of symmetry. And the axis of symmetry is right through that vertex, where it should be. I don't do well. Oh, undo. Where's my undo button? Wasn't that my undo button? There we go. It's the undo button. There we go. It would look like this. Okay, what would this equation be in vertex form? E of x equals, what's my a? 2 times
X
X plus 1.
minus squared.
Good. And could you name all the characteristics? Yeah, you could. All right, last one we're going to do together today is number 8. All right, and this there, that negative b over 2a thing that helps us find the vertex is so handy because, well, we know that the vertex is either the maximum or the minimum point of the function. We know that the maximum value of the function happens at the vertex or that the minimum value of the function occurs at the vertex. This problem says a record label uses the following function to model sales of a new release. A of t equals negative 90t squared plus 8,100t. The number of albums sold is a function of time in days. On which day would the most albums be sold? What is the maximum number of albums sold on that day? So we know that this is a quadratic function. It's squared. How is it opening? Downward. So the vertex would be the maximum value, wouldn't it? So to find the x value at the vertex, which for us is going to be t, do you see that t is our independent variable? We're going to do negative b over 2 times a. And when we do negative 8,100 divided by negative 180, we get that t is equal to 45, which in our case would mean 45 days. So that means we sell the most albums because that's our maximum point, because this one opens down 45 days after the release of the album. What is the maximum number of albums sold on that day? How could we figure that out?
Again, 45.
Plug 45 into the function. And since most of you are not sitting there with a calculator, when you plug 45 into the function, you get out 182,250 records are sold 45 days after the release of the album. Okay, does that make sense? All right, your homework is out of your textbook. It's problems 16, 17, 20, 22, 23, 27, and 29. All those are graphing problems. So graph them and give us the characteristics. But then on just 16, 17, 23, and 29, write it in vertex form. You don't have to write them all in vertex form, but we picked out a couple. And then 30 and 33 are, those are word problems. These same instructions are on the calendar that I have posted on the website. So you can either come take a picture of the board, you can write it down, or you can pull it up off the website.